Okay, so in Jahn-Teller distortion, you can have a unsymmetrical distribution of electron in a octahedral geometry, especially
EG orbital.
yes, EG orbital is a very responsible orbital for Jahn-Teller distortion. Now see, these all things we have already completed. Crystal splitting, which factors that affect on, you can say various particular crystal field splitting energy. So after that, then next is Jahn-Teller distortion. So see, Jahn-Teller distortion is basically, it is for a non-linear molecule in which, is the screen is visible?
Yes, sir.
Okay, so it is for a non-linear molecule in which you can have a electronic degeneracy is there. So non-linear molecule in an electronic degenerate state, distortion must occur to lower its symmetry and to remove the degeneracy. So that's why splitting is take place. दो रीजन है यहाँ पे Jahn-Teller distortion होने का. One is to lower its symmetry and दूसरा जो है that is to remove the degeneracy. तो जो 5 d orbital है उनकी एनर्जी सेम है. So if you remove degeneracy, so that orbital is having different energy and they are splitted into different set of orbital. So for non-linear molecule in a electronic degenerate state is unstable and therefore it undergoes distortion. So two things take place. One is lower the symmetry and another one is remove the degeneracy. So as a result, it's lower its energy and increase the stability. Okay, so that is called Jahn-Teller distortion. So degeneracy means you know that once one electron is there in d1 orbital, so it may be in d orbital, so it may be fill up in any of the orbital because all the orbital having same energy. Okay, but d3 is there, so it is equally filled. So this is called singly degenerate. Singly degenerate, but here this is called triply degenerate. So how can this degeneracy is removed? So this is removed by tetragonal distortion. That means distortion along which axis?
Z.
Along z axis. So two things take place. Either bond length along z axis is increases or bond length along the z axis is decreases. So as a result, this ligand interact less with those of orbital having d component, especially dz square, dxz and dyz, with resultant stabilization of orbital. So energy of that orbital become decreases. So in this way, distortion which is taking place in the molecule. So you know that see, you can have a either two ways you can do the Jahn-Teller distortion. One is in the case of octahedral complex. In the case of octahedral complex, if either EG orbital or you can say T2G orbital is unsymmetrically filled, then you can have a Jahn-Teller distortion. If EG orbital is unsymmetrically filled, then there will be strong Jahn-Teller distortion. And T2G orbital is unsymmetrical field. So at that time you can have a weak Jahn-Teller.
हेलो सर
सर शायद आप लिख रहे हैं लेकिन दिखाई नहीं दे रहा.
Okay, fine.
यस सर
Sir,
फ्रीज हो
past
गया
page
स्क्रीन.
is showing. Past page is showing.
Okay, fine, no problem. I will share my screen again so you can better way know it. Okay. Just wait for a few minutes. दो मिनट आप रुकिए, है ना, एक फोन है ना, मैं अटेंड कर लूँ, उसके बाद कंटिन्यू करते हैं।
ओके सर।
Okay. So now I share my screen again so you can clearly see it. Now it is okay. Is it okay?
Yes, sir.
Okay, fine. So see, in an octahedral complex, you can have a e orbital, which is orbital, which is unsymmetrical field. So at that time, there is no Jahn-Teller distortion. Sorry, strong Jahn-Teller distortion. Hello. Okay. And second one is T2G orbital is unsymmetrically filled. So at that time, you can have a weak Jahn-Teller distortion. This is the case for octahedral complex. But for tetrahedral complex, what happens? For tetrahedral complex, if you having Eg orbital is unsymmetrically filled, then at that time there is a weak Jahn-Teller distortion, and T2G orbital, only T2. Of course, there is no symmetry with tetrahedral geometry. So T2 orbital is unsymmetrically filled. At that time, what happens? There is a
Jahn-Teller distortion.
Strong Jahn-Teller distortion. At the time, strong Jahn-Teller distortion. Okay, this is the case where you can have a strong Jahn-Teller. Here it is having weak. Now again, see, Jahn-Teller distortion is of two types. That is tetragonal elongation and compression. Okay, so if along z-axis bond length is increases, then what we call it?
Elongation.
Elongation. So it is called z out. Z out means
in compression.
bone length along z-axis is increases. What happens in z in?
Compression.
Bone length along z-axis is decreases. So two things take place. So when you are getting Z in, so Z in is a special case where T2G having either one electron or T2G having 4 electron. Okay, T2G having either one electron or you may have a 4 electron. That means after 3 it is a half fill, and then 4th electron is come, so it is a T2G one type arrangement, similar arrangement. So in these two cases Z in is take place, and rest of the whole case, okay, in remaining case there is a Z out. This is the case where you can have a Z in. Okay, in other cases it becomes Z out. Is it clear?
Yes, sir.
Now we take one example of particular system. Suppose your complex is a octahedral complex with, see, D1 configuration is there and ligand is a strong field, and also you can have a weak ligand. In both the case you can compare it. What's about ZD?
Z.
Just we look at it. See, in case of D1, which orbital field first? T2G. Yes, so you can have a one electron in T2G. Eg orbital is having 0, so it's a, of course, weak or strong? It's a Z in. Distortion is weak, because
Both will be Z in.
yes, whenever there is unsymmetrical field T2G, at that time weak distortion. For a case of EG unsymmetrical, you can have a strong Jahn-Teller distortion. Now weak field ligand is there, so at that time you can have a D1 configuration. So one electron gets occupied in again in T2G. EG remains vacant, so you can have a Jahn-Teller distortion, but it is again Z in and it is weak. What is the case of D2? In strong field ligand, this is arranged in this way. This is called T2G2.
Z in.
Okay, and EG 0. it is again, it is sorry Z out. See, Z in दो ही केस में आएगा, T2G1 and T2G4. Okay, in rest
Yes.
of the case it is Z out. Now see T2G unsymmetrical है, so again there is a weak Jahn-Taylor distortion. यहाँ पे भी दो इलेक्ट्रॉन ऐसे आएंगे. It is also T2G2 is 0. You can also have a Z out with weak Jahn-Taylor distortion. Okay, so this is the case of, you can have a weak Jahn-Taylor distortion. Okay, now what happens if you go for D3 configuration? If both the orbital is symmetrically filled, then there is no Jahn-Taylor distortion. If you having 3 electrons, that
Sir,
is
Z
N
in or Z out is experimental.
what? Z?
Sir, Z in or Z out is experimental.
Z in and Z out is a, of course you can decide it theoretically. It is a kind of arrangement where you can, of course it is earlier it was proposed from experiment, but now on that evidence the theory was set up, and for that conclusion is come out where you can have a T2G1 and T2G4 shows Z in, and in rest of the case you can have a Z out. ओके, सो अभी हमको अभी प्रैक्टिकल की जरूरत नहीं है, अभी हम थियोरेटिकली डिसाइड कर सकते हैं बाय लुकिंग इट
और
कॉन्फ़िगरेशन.
टेट्राहेड्रल एंड ऑक्टाहेड्रल दोनों के लिए T1G और T1 एंड T4 है.
जेड इन के लिए सी दोनों के लिए वो तो सेम ही रहेगा, बट उस केस में तो केस ये पेयरिंग का केस आएगा ही नहीं, तो उसमें सिंपली आपको
यस सर.
आई स्पिन ही लिखना है ना, उसमें स्ट्रॉन्ग लिगेंड नहीं आएगा, पेयरिंग तो आएगा नहीं. बट T2G1 है और T2G4 वो दोनों में रहेगा जेड इन में. So what's about D3 configuration? D3 orbital is, yes, it is complete, it is half fill configuration T2G3. Sorry, this is not correct one, because here I have written electron with I spin that is remains unpaired, but you want electron which is in pair. So this is the correct one. It's a T2G3 EG0. Here you can have a Z out, and it is a weak, because see T2 orbital is unsymmetrically filled. But what is the case with weak ligand?
There will be 0.
Yes, it is a high spin complex, so all the electron remains singly occupied. It is a half filled, symmetrically filled configuration, and therefore you cannot have Jahn-Taylor distortion. So here there is no Jahn-Taylor distortion. Okay, there is a no Jahn-Taylor distortion. What's about D4? चलो D4 में here it's a T2G4. Yes, it's a Z in. EG remains vacant. It's a T2G4. So Z in with weak Jahn-Taylor distortion. What's about high spin complex? You can have a fourth electron in EG orbital. So EG orbital
Strong.
is unsymmetrical field.
Strong.
So it's, yes,
J.
it's a strong Jahn-Taylor. It's a Z out. It's a Z out. T2G3 है देखो. T2G4 और T2G1 केस में Z in आएगा.
Yes, sir.
So it's a strong Jahn-Taylor distortion. Now what's about D5? अगर strong ligand है तो T2G unsymmetrical रहेगी. Okay? EG having 0 electron. T2G is unsymmetrical. EG having 0 electron. So you can have a Z in, and it is weak Jahn-Taylor. What's about Z out? Sorry, Z out, and it's a weak. What's about I spin complex?
0, because none of our EG orbital is symmetrical. Yes.
So both the orbital are symmetrically filled. It's a T2G3 and EG2. So you can have a no Jahn-Taylor distortion. What is the case of D6?
Symmetrical. T2 orbital will be symmetrical.
So this is T2G6. It's a symmetrical one. So there is no Jahn-Taylor distortion. And in this case, what happens? If weak ligand is there, then you can have a T2G4.
Weak jet out.
See, look at this configuration. It's a T2G4, EG2.
Z.
Yes, it's a JD. T2G4, so it's a JD and it is weak. Okay. Is it clear up to here?
Yes, sir.
Okay. So now we take one more blank slide to. So see, in short, you can have a T2G1 and T2G4. This is the two cases where you can have a Jahn-Taylor distortion, which is gives Z in rest of the case it is Z out. So again, in octahedral complex, if you're having D7 configuration, then what happens? Octahedral complex with D7 configuration, then you can have a strong ligand is there, or it may be weak ligand complex, high spin complex. This is for low spin complex. So here you can have a T2G.
Strong jet in. Jet
Yes.
out. Strong.
Yes, it's a T2G6 EG1. EG orbital is an unsymmetrical field. So you can have a strong Jahn-Taylor distortion. Strong JTD. That is Z out. And if you having weak ligand, so electron remains unpaired. These are the 5 electron, then 6, 7. So it's a T2G 5 times, EG 2 times. So it's a Z out, and again it is weak. Okay, it's a weak Jahn-Taylor distortion. What's about D8 configuration? If configuration is D8, then you can have a T2G.
Weak.
Okay.
Jet out.
All the electrons are paired in T2G orbitals, and 2 electron remains. Sorry, 2 electron with pair in EG orbital. So you can have a EG is unsymmetrical. So what happens in this case? Z in or Z out?
Jet
It's
out.
a Z out. Yes. So here you can have a T2G6, EG2. It's a Z out with weak distortion or strong.
Weak.
It's a weak, strong Jahn-Taylor. Why it's a strong? Because new stroke है Jahn-Taylor. Reason is EG orbital is unsymmetrical field. Okay, so that's why it is. You can have a strong Jahn-Taylor. What's about in high spin complex? Electron remains unpaired, so you may have a first 5 electron with up spin and then remaining 3 with down spin. So you can have a see T2G is a completely symmetrically filled. EG orbital is also symmetrically filled. So what's about Jahn-Taylor distortion?
0.
0. Yes, there is no Jahn-Taylor distortion. No JTT. Yes. What's about the 9 configuration? See, the case of copper is very good familiar in octahedral complex. Although octahedral complex of copper they show strong Jahn-Teller distortion. Okay, so you can take that case. Case of the octahedral complex of copper is a very familiar for Jahn-Teller distortions. So what happens if you having a 9 electron? How they are filled?
Unsymmetric electron in EG orbital.
Yes, so if strong field ligand is there, so they get arranged with pairing. So T2G orbital got 6 electron and the remaining 3 electrons with EG orbital. So you can have a T2G 6 times EG 3. So EG orbital is unsymmetrical one, so it's a strong Jahn-Teller distortion with Z out nature. At the same time, if D9 is there, again the case is electron remains unpaired.
Same, there will be same.
Yes, and that's why this case of copper complex is a very good familiar for Jahn-Teller distortion. It's a T2G6. Some configuration is there, EG1, and therefore whether the ligand is a strong field or weak field, you can have a strong Jahn-Teller distortion. It's a strong Jahn-Teller distortion. It is called Z out. In the case of D9 configuration, there is no Jahn-Teller distortion. The reason is it is symmetrically filled. Yes, both the orbital are symmetrically filled, so there is no Jahn-Teller distortion. What's about in tetrahedral complex? So tetrahedral complex it is a high spin complex. It is always high spin complex. So electron remains unpaired. And second thing regarding tetrahedral complex is which orbital fill first? In the case of octahedral, it's a T2G.
E.
But here E orbital good. E orbital fill first. So you can have a E orbital and then followed by T2 orbital. This is a E orbital and this is a T2. So if D1 is there, so one electron gets accumulated in E orbital, accommodating. So what's about Jahn-Teller distortion?
JD.
It's a weak distortion, weak Jahn-Teller distortion. Because in the case of octahedral complex, if G orbital is unsymmetrical, so you can have a strong Jahn-Teller. But in the case of tetrahedral complex, T2G is unsymmetrically, then you can have a strong Jahn-Teller. So here it's a weak Jahn-Teller. Again, it is not a T21, so it's a Z out. Okay, which type of nature is there? It is Z out. What's about D2? So 2 electron remains in this way. In both the orbital there is one electron. So E orbital is symmetrically filled. So what's about Jahn-Teller distortion?
0.
0. It's a 0.
सर Z in मतलब dz स्क्वायर की एनर्जी नीचे हो जाए, कम हो जाना ना.
जेड इन का मीनिंग ये है कि इनकी जो कंप्रेशन होगा तो जेड जो बॉन्ड लेंथ है जेड एक्सिस वाली वो कम हो जाएगी. जो आपकी जेड एक्सिस है सो वो बॉन्ड लेंथ है वो नॉर्मल बॉन्ड लेंथ से विल बी डिक्रीजेस फ्रॉम नॉर्मल बॉन्ड लेंथ, कम हो जाएगी, है ना. नॉर्मल बॉन्ड लेंथ है वो इंक्रीज होगी, सो दैट इज वी कॉल इलोंगेशन. कंप्रेशन मींस नॉर्मल बॉन्ड लेंथ इज डिक्रीजेस.
ओके.
तो दो केस में वो पॉसिबिलिटी है, एक T21 में और दूसरा जो है वो T24. बाकी सारे केस में इलोंगेशन होता है. इलोंगेशन इज मोर कॉमन. So now there is no Jahn-Teller distortion. What's about D3?
Z out.
Yes, it is not Z out. See, look at configuration. Yes, it's a T2 having C 1 electron, E having 2 electron. So it's a Z in, and it is a strong Jahn-Teller because here T2 orbital is unsymmetrical field. What's about D4? For D4 configuration, you can have again T2 orbital is unsymmetrically filled, so it's a strong John Taylor distortion and it is Z out. But case for D5 is there any John Taylor distortion in D5?
Symmetrical, 0.
It's a 0. So there is no John Taylor distortion because both the orbital are symmetrically filled. So there is no John Taylor distortion, no JTD, because both the orbital are symmetrically filled. Now in the case of D6 configuration, what happens? In the case of D6, which orbital is symmetrically filled?
EG,
E orbital, yes, it is. That is not used for tetrahedral geometry. So it's a E3, T2, 3. So it's a weak John Taylor distortion. It is Z out. Similar way in the case of D7 configuration, you can have a E set and T2 set. How electron gets arranged? Seven electrons are there, so this is the way 7 electron gets arranged. Is there any John Taylor distortion?
no, symmetrical.
Both are symmetrically filled, so there is no John Taylor distortion. What's about in D8? This is a D8, arrangement
Strong.
in the D8.
Z out.
T2 4 and E is 2, E is 4, so it's a Z E. It's a strong John Taylor. T2 4 है जो, so T2 4 is there, that at that time you can have a ZE. Here it is having strong John Taylor. What's about D8? Sorry, D9 configuration? In the D9 configuration, so this is a D9 configuration where you can have a T2 orbital is unsymmetrical field.
Strong. Z
Yes.
out.
So there is a strong John Taylor distortion. Strong John Taylor distortion. And it is a Z out. What's about D10? There is no John Taylor distortion. It's a 0. Good. So see, this is about John Taylor distortion. Now, after that, then see ligand field theory. Go to next topic, that is ligand field. Is there any doubt in John Taylor distortion? So basically, why John Taylor distortion happens? Only the reason is to lower the symmetry and increase the stability, remove the degeneracy, and that's why John Taylor distortion is take place.
सर एप्लीकेशन ऑफ सीएफटी नहीं है?
एप्लीकेशन ऑफ सीएफटी वो 10 DQ कैलकुलेशन वो सब देखा ना उसमें.
अच्छा सर वो वाले सर, यस सर, नेक्स्ट वाले.
हाँ कलर या तो वो सब उसमें ही चल रहा था. अभी जो है उसका वर्ड लेके वेवलेंथ भी कैसे फाइंड आउट करेंगे, एक दो एग्जांपल ये भी लेंगे इसके बाद. But see now what is ligand field theory? Before that we see the two important theory. Ligand field is very close to crystal field theory. It is nothing new. So ligand field theory and molecular orbital theory. Unfortunate valence bond theory is not there in your syllabus. Otherwise you may decide hybridization of complex using valence bond theory, but that is not there. But here it is Ligand field theory is basically nothing but you can have a it is similar to crystal field. See, crystal field theory only include ionic interaction in the solid. There is no covalent interaction. MO theory develop and apply only to non-metal complexes. So ligand field theory is a combination of both transition metal as well as coordinate compound. Transition metal coordinate compounds, and it includes both especially ionic interaction as well as covalent. But molecular orbital theory for octahedral complexes is there where donor atom, that is atom especially ligand with a p orbital or hybrid orbital directly approaching the metal ion to form sigma bond. So thin orbital had dxy, dyz and dxz orbitals. They are not of correct symmetry to form sigma bond. But dx square minus y square, dz square, px, py and pz and s orbital are all have a correct symmetry for interaction with ligand, especially for sigma bond formation. Okay, in order to getting sigma bond, so this is the orbital which is having correct symmetry. So they are only involved in the sigma bond. In MO theory, that will be of course discussed in detail how sigma bond is formed, how pi bond is formed. But see, ligand field theory ultimately behaves in the crystal field splitting, same way here it is there. Ligand field theory assume only the interaction between metal and ligand, and it is a purely ionic, but that is a drawback of ligand crystal field theory, or you can say ligand field theory. There is not only pure ionic interaction, so that is overcome in molecular orbital theory that we will take later. But 5d orbital in isolated metal in a free metal state are non-degenerate, so they are having same degeneracy. So if it undergoes splitting, so as a result, degeneracy is removed and you are getting splitting with orbital with some set having higher energy and some set having lower energy. So metal ion when surrounded by ligand or negative ions, at that time that sphere is contracting towards the metal, or you can say this sphere gets contracting towards metal. See, so as a result, repulsion between negative field and the negative electrons of metal, negatively charged electrons of metal and negative field, and because of this repulsion it causes energy of all the d orbitals to rise, but rise is equally. For some of the orbital में having energy gets altered to decreases. रिपल्जन वाली ऑर्बिटल होगी उनकी एनर्जी इंक्रीज होगी सबकी एक साथ, जो रिपल्जन नहीं है उसमें वो डिक्रीज होगी. सो इन दिस वे सी ऑर्बिटल गेट्स स्प्लिटेड फ्रॉम एवरेज एनर्जी. सो इन रियल लाइफ वी कांट हैव
ये आयनिक तो सीएफटी बताता था.
सीएफटी में आयनिक है ना, जो कोवेलेंट है उसके लिए मोलिकुलर ऑर्बिटल थियरी है.
सर एलएफटी एंड सीएफटी सेम है क्या?
लिगेंड फील्ड एंड क्रिस्टल फील्ड थियरी ऑलमोस्ट जो स्प्लिटिंग सारी चीजें उसमें हमने सीएफटी में देखा वो सेम चीज यहाँ पे है, सेम ही है. बट थोड़ा जिसमें जो है लिगेंड अप्रोचेस होता है, इसलिए इस थियरी को हम लिगेंड फील्ड बोलते हैं. क्रिस्टल फील्ड थियरी है चीज है कॉमन थियरी, दोनों में से ये ऑलमोस्ट सेम ही है, कुछ उसमें डिफरेंस नहीं है. सी यहाँ पे आपको देखो लिगेंड को आप प्राइम रख के आप थियरी डिस्कस करते हो, सो इट इज ए लिगेंड फील्ड. सो दे आर वेरी क्लोज, ओके सेम ही, इसलिए मैंने यहाँ ब्रैकेट में भी लिखा है कि इट इज ए लिगेंड फील्ड थियरी इज नथिंग बट क्रिस्टल फील्ड थियरी, दैट इज वी हैव ऑलरेडी डिस्कस. एमओटी एक डिफरेंट है, एसएम है. तो इसमें क्या होगा, सी 6 लिगेंड अप्रोचेस टू फ्री मेटल आयंस इन octahedral field. So what happens? Splitting is take place. We know that in octahedral 2 set is having higher energy and T2 is having lower energy. This thing we have already completed. That is there in ligand field. क्रिस्टल फील्ड में हम क्या करते थे, CFSC क्रिस्टल फील्ड स्टेबलाइजेशन कैलकुलेशन करते थे ना. सेम वे यहाँ पे आप लिगेंड फील्ड स्टेबलाइजेशन एनर्जी कैलकुलेट कर सकते हो. ओके, व्हेन वन इलेक्ट्रॉन इज एडेड इनटू ऑक्टाहेड्रल फील्ड, वो सेम वे जो उसमें जो मेथड यूज की थी वही मेथड यूज करना है. high spin complex here, so electron remains unpaired. Okay, and then you can predict which one is a more stable conformation. अगर ऑर्बिटल हाफ फिल है तो वो स्टेबल हो गए सारे में से सी दिस इज स्टेबल half fill orbital fill up so that configuration is stable, so you may got ligand field stabilization energy. Difference in energy between T2G and EG orbital is relatively small, and also pairing cost energy, or you can say so it needs to determine which cost less putting the electron in EG orbital or pairing with electron already in T2G orbital. दो चीजें हैं, या तो इलेक्ट्रॉन T2G में EG में जाएगा या तो T2G में पेयर हो गए, तो उसके लिए पेयरिंग एनर्जी है, वो सारी चीजें हमने ऑलरेडी डिस्कस किया है, दैट इज फॉर सेक ऑफ योर नॉलेज. पेयरिंग एनर्जी है वो अगर क्रिस्टल फिर स्प्लिटिंग एनर्जी से ज्यादा है सो इलेक्ट्रॉन रिमेन्स अनपेयर्ड, एंड वो कम है तो पेयरिंग होगा. ओके, सारी चीज कैलकुलेशंस वी हैव ऑलरेडी सीन इन CFT, वो दोनों सेम ही है. For high spin complex, electron remains unpaired. You can calculate CF ligand field stabilization energy in this way. So this is almost similar, and this is the result of crystal field effect for weak and strong octahedral complex. So in this case, there is a pairing energy is higher. So this is a case of high spin complex where electron remains unpaired. And here there is a pairing energy is lower, so this is the case of low spin complex. CFSC है, दोनों सेम ही है, कोई डिफरेंस नहीं है. Is it clear? Okay. Now see यहाँ पे आपको सिर्फ नेम LFSC आप देंगे, ligand field, बाकी कुछ नहीं है, सेम ही है. One more see evidence is there for ligand field stabilization energy is the first evidence for such energy might be important in transition metal complex, and that is comes from examination of its lattice energy. And see, lattice energy is inversely proportional to radius, ionic radii especially. So when ionic radii is decreases across the first transition row, what happens? If you go yes, if you go along the row, so radius is decreases. As a result, what happens? Increasing in energy. So that's why, however, it is curve is not smooth, and only Ca plus 2, Mn plus 2, and Zn plus 2 fall on the theoretical straight line. This is just theoretical straight line. So almost what happens if you go from calcium to scandium, titanium, this is a 3D series. So this is increases, the energy is increases. But two cases are there where this curve gets fall. In the case of Mn, and second one is in the case of Zn. What is the reason to have a less energy in these two cases?
Repulsion between electrons in the
वो तो है ही जो आपने बताया, जैसे रिपल्जन ज्यादा इलेक्ट्रॉन हो गए तो, बट एनर्जी कम क्यों हो रही है? रिपल्जन है तो बढ़ना चाहिए एनर्जी. सो D5 है, इट इज जैसे आप फिल D5 कॉन्फ़िगरेशन जो आप फिल
E2 और E दोनों में है ना सर, तो जब इलेक्ट्रॉन नीचे आ रहा है, फिर जब ऊपर रहेगा तो लिगैंड अट्रैक्ट करेगा.
सी से होगा. सी आपके पास D5 है तो उसमें क्या होगा? 5 इलेक्ट्रॉन गेट्स रिमेन्स अनपेयर्ड इन दिस वे. So it may be d orbital is half fill, or you can have a d orbital which is completely filled, D10. So completely filled configuration and half fill configuration is extremely stable. This is stable, and as a result, you can have a, because of this stable configuration, its energy is lower. Okay. So stability is the factor. Is it okay?
Yes, sir.
Okay, now these are the C value for D1 and D6 configuration. It's a minus 4 dq. D2 and 7 it's a minus 8 dq. 3 and 8 it is minus 12 dq, and this is minus 6 dq. So you can calculate it and compare with this data. You can calculate C lambda max using 10 dq value simply. This delta is nothing but energy gap is a 10 dq. or you can say it is crystal field stabilization energy. So if lambda is given to you, or you can, if you knowing the CFSC or 10dq value, then you can calculate lambda simply by putting the value of Planck constant h and velocity of light c. So you can get lambda. Okay, so this is the one of the example here. See, lambda is given to you, so you can calculate crystal field stabilization energy. So this is about ligand field theory, or you can say crystal field stabilization theory. Now, see, very important theory is molecular orbital theory, because earlier two theory where we have not discussed about pi bonding, but here this theory include sigma bond as well as pi bond. Valence bond theory only explain electronic property. Crystal field theory only explains spectral property. See, this is explained by crystal field theory. This is explained by valence bond theory. And molecular orbital theory, this theory is very important theory to explain how orbital gets overlap, how molecular orbital gets formed from individual or set of the ligand group orbital and atomic orbital of metal. So you can explain magnetic properties, you can explain its color spectra. Okay, so many properties are there, so that can be explained using molecular orbital theory. If you draw a MO diagram and find the unpaired electron, then you may predict whether this material is paramagnetic or diamagnetic. You can also calculate magnetic moment. So this theory is based on the purely covalent as well as purely electrostatic model, and all possible intermediate situations are considered in this theory. So individual atom is combined to form molecular orbital, and this orbital involved for bonding should have a similar energy. Then they get overlap in the same region. Okay, so symmetric properties discussed with this theory. Symmetric properties of combining orbitals should be matched, that is required. Same symmetry orbital can combine with each other. That is very important, that is required. Number of molecular orbitals formed will be equal to the same number of atomic orbitals. Remember, जितनी atomic orbital है उतनी ही molecular orbital form होंगे. Okay, it is similar. So this theory explains covalent bonding in complex. Covalent bond formed by linear combination of petal atomic orbitals and ligand group orbital. Similarities of ligand group orbital must match with the, or you can say symmetries, particular symmetry of ligand group orbital and metal orbital. They get matched with each other. At that time, you can have a positive overlapping. Otherwise, overlapping does not take place. Okay. When the covalent bond is formed, what is requirement? In order to have a covalent bond,
Head on head overlapping.
yes, metal atomic orbital and ligand group orbital having same symmetry, then they get overlap and it will form. That is called positive overlapping, and you can have a covalent bond. Now look at here, sigma bonding in tetrahedral complex. How this sigma bond is formed? So see, this is the case where ligand approaches to metal on x, y, and z axis. This is your z axis. This is x and this is y. So ligand group orbital will overlap with metal orbital along octahedral bonding axis to form sigma bond. This is the sigma bond between ligand and metal. So here sigma bond is very common. Now, which orbital is responsible to form sigma bond out of this three set? One is 4s, another one is 4p, and 3d orbital. So out of this set of the orbital, there are 9 orbital. One is 4s, 4p orbital is 3 in number, and 3d orbital is 5 in number. So all these 9 orbital cannot form sigma bond. Okay, so for that, 4s orbital is responsible to form sigma bond. 4s orbital having symmetry is, or s orbital which is transformed into A1G. Symmetry of s orbital is transformed into A1G in octahedral complex. Symmetry of p orbital is transformed into T1U. This is the T1U. This is A1G. And T1U is a symmetry of p orbital. And d orbital is of two set, T2G and EG. So dxy, dyz and dxz is transformed into T2G set. And dx square minus y square and dz square is transformed into EG set. So now EG orbital, that is you can say dx square minus y square and see T2G. So here T2G orbital, that is dxy, dyz and dxz. These orbitals lies between the axes and are not capable of overlapping with ligand orbital to form sigma bond. This orbital cannot form sigma bond, T2G set. They get, what happens? They lies in between the axis. But see, two orbitals are there which is along the axis, that is the x square minus y square and dz square. That is called T2G set, or you can have a T1U set. So these orbitals are pointing along the axis and they can form the sigma bond by overlapping with ligand group orbital. A1G orbital is spherical in shape. It is just a spherical shape, and therefore it can overlap with ligand group orbital along the axis, and therefore it can also form the sigma bond. Okay, so out of this all possibilities, out of these 9 orbitals, only 2 orbitals, that is dx square minus y square and dz square, that is, you can say, sorry, here T2G is there, that is in x and y. So you can have a, see, this T2G set cannot form sigma bond. Rest of the other, that is called EG set, can form the sigma bond. Here T2G orbital which is lies in between the axis and therefore it cannot form sigma bond. So out of this 9 orbital, these 3 orbital, that is dxy, dyz and dxz cannot form sigma bond. Rest of the other orbital are form sigma bond. So what are the orbital which are available for sigma bonding? One is A1G, yes, it is comes from s orbital. Then T1U, it is comes from p orbital, and EG orbital, it is comes from d orbital. So you can have a 1 plus 3 plus 2, that is 6 orbitals. They are available for sigma bonding, and rest of the 3 may form the pi bond. So T2G orbitals lies in between the axis, and therefore these orbitals are not capable of overlapping with ligand group orbital to form sigma bond, and they are considered to be non-bonding orbital. तो जब आप हम molecular diagram draw करेंगे, so we keep this T2G orbital is a non-bonding. It cannot form a molecular orbital. Okay. So tomorrow we will see the molecular diagram of this octahedral complex, and we will also see the what is the molecular diagram for a compound having pi bonding. It will be 2 type again. Pi donor ligand is there and pi acceptor ligand is there. Yes.
Sir, can you share the sample questions?
Yes, definitely. I will share you full question bank, but you just wait for 1 or 2 days. Once this weekend is comes, so I will share the question banks after verifying it.